Good morning. Thank you for joining us at the Calculus Reading Group. Today I have the pleasure of introducing Maria Goronova from the University of Edinburgh. She will present her recent work on automatic reparameterization. Her work has a number of connections to calculus, so I'm really looking forward to this talk. I first became aware of Maria's work at the Principles of Programming Language conference 2 years ago, where she presented domain-specific language called SlickStan, an extension to Stan. And this uses Hamiltonian Monte Carlo and differentiable inference to approximate a density function. More broadly, she has interests in programming, learning to program, and human-computer interaction. I think this is a really great opportunity to meet and discuss with a researcher on the cutting edge of probabilistic programming languages. Without further ado, will you please join me in giving a very warm welcome to Maria Goronova.
Thanks very much for having me. This was a very nice introduction, so it's really nice to be here, and I hope this is interesting to people. It does indeed have connection to calculus from several different ways. So hopefully it will be interesting. So should I share screen then? Okay, is that visible?
Yes, looks great.
Okay. So again, thanks very much for having me. Today I'm going to talk about some work that I did with Dave Moore and Matt Hoffman, which is on automatic reparameterization in probabilistic programming. And I'm going to start, I'll have to kind of like unfold a couple of different concepts, but feel free to interrupt me if anything is unclear. I'm happy to keep this very conversational. The only problem is that I don't see you. I only see my slides. So you'll have to kind of possibly rudely interrupt me if you have a question, which is okay by me, is what I'm saying. All right, so I'm going to start by, I'm going to start by just a very quick overview of what we understand by probabilistic programming here. For this particular work, we're going to think of a probabilistic program as a generative model where we're going to generate some random variables from some given some prior, and they might depend on each other and so on. And then we're going to say how some data, in this case y, that we're interested in is generated, how we believe is generated from these parameters. And then we observe the data. And the goal is to, in a sense, invert this process. So we've started from, let me grab the pointer. So we started from the parameters, and our program describes how our data, in this case y, is generated based on these parameters. And then at the end, we observe some value for y. And now we want to work backwards and say, infer what the posterior distribution given these observations is over the parameters. Okay, and so for the rest of the talk, we're going to see what is reparameterization, what is model reparameterization, how do we do it, and why is it difficult. We're going to see what it looks like in the context of probabilistic programming and how we can use the fact that we work with probabilistic programs rather than just some density that we defined in a Python function. How we can use this, to our advantage. And finally, I'm going to introduce the main contribution of this work, which is a way to use gradient-based methods to find out a good reparameterization. Okay, so The goal of probabilistic programming, as I mentioned before, is really to do this inversion process when we infer a posterior distribution in an automatic way, right? We are only going to provide this program over here as a user, and then we hit run and we get some posterior over the parameters automatically. But the problem is that this can rarely be actually the case in practice. And the reason is there are a lot of black box inference algorithms that can do this. You can give them a general program or maybe program with some constraints and they can run inference on it. But the quality of the inference is going to depend hugely on the shape of the actual distribution that we're working with. So let's see the following example. Here we have a very simple model where X and Y are strongly correlated. And this is what their joint distribution looks like. Now, forget for a second that we can just sample Y from normal 0, 1, and then sample X from normal Y 0.1, right? Like, forget about this. Let's say that we want to use a general purpose algorithm to sample from this joint density. And one such algorithm, for example, is a very simple algorithm, Metropolis Hastings, where the idea is that we are going to infer this distribution by sampling repeatedly from it. And the sampling works by, we start from some current sample point, let's say this one here. You do see my laser pointer, right?
Yes, we can see that.
Okay, perfect. So let's say we start from over here. This is a sample from the distribution. And the idea is let's to propose a new sample somewhere in the neighborhood of the current one. Let's say this one. And then based on how likely it is, if the original sample was in part of our distribution, then this one is part of our distribution. So based on this probability, we decide if we're going to accept or reject it. And if we reject it, we come back here and we do this again for another random sample. And if we accept it, we instead come here and then do random step here and so on. And the way this looks like is that we're going to just like very like slowly explore this distribution like that. We're just gonna randomly walk around this distribution and collect these samples from the distribution, and that's going to approximate our entire distribution. The problem with Metropolis Hastings in this particular case is that we need to decide based on a sample, let's say here, how far are we going to try to propose a new sample? How big the step that we're going to try to make is going to be. So we can decide that we're going to do a big step because we want to more efficiently, like we want to try to reach further out in the distribution. But in this case, if we do a big step, there is a very big probability that we're going to end up somewhere over here, right? A much smaller probability that we're actually going to, because it's a random step, so there is much smaller probability that we're actually going to land somewhere where there is high density. So we're going to keep rejecting. We're going to do this. Propose that, reject. Propose that, reject. Propose that, reject. So we're forced to do very little steps, and that's going to look like that. Like we're just going to explore this very, 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 very slowly. And that's not good. That's inefficient. It's going to take a very long time for us to sample from this and so on. And now you might be thinking, okay, that doesn't sound very smart though. Like surely we can do something smarter. And yes, we can. So another thing that we can use is, and which is what we use later in this work, is Hamiltonian Monte Carlo. And I'm just going to recap very quickly HMC in case people are not familiar with it. The basic idea is that we're going to imagine our density as some surface, some multidimensional surface. And then we're going to put a minus sign in front of it and flip it around. And now what happens is that the valleys in this surface are regions of high density, while the hills are regions of low density. We're going to put a particle, this is this thing over here, we're going to put a particle somewhere, and that the position of this particle defines a sample from the distribution. And then we're going to kick it. We're going to give it a little momentum in a random direction. Here is this arrow over here. And we're now going to simulate the trajectory that this particle is going to take for some time. There are no other forces here. This is very simple physical system, no other forces. So this will just like keep moving. And we're going to simulate this for some time and then stop. And this is our proposed sample. So here we, in a way, we use the gradient information of the density, the underlying density, to explore more efficiently, because we're going to naturally move towards regions of high density and not so much towards regions of low density. And the other thing that's great about this algorithm actually is that if this simulation was perfect, we can prove that we don't even have to this proposed sample that in Metropolis Hastings we will either accept or reject. Here, we don't even have to do that, because if the simulation was perfect, we will always accept this. This sample is always going to be a sample from the distribution if this is a sample from the distribution. Of course, in practice, we can't simulate this exactly, and we use numerical integration methods. In the case of HMC, that's usually the leapfrog algorithm. Okay, that looks great. And if we go back to this, to this problem, and imagine that we're using HMC, things will look much better, because obviously the gradient in this direction, so if we start here, the gradient in this direction is bigger than the gradient in this direction. So we're going to tend to gravitate towards this region of high density, and this will be much easier to explore. However, HMC has its own pathological examples, unfortunately. And we see on the right one such very famous example that is called in the literature News funnel. And the idea here is that X and Y, there is a very, very strong nonlinear dependency between X and Y. And the density looks like this funnel where the upper bit of the funnel is very flat. The curvature there is very low, but there is this funnel bit where the entire density curves very strongly, and more strongly the more down it goes. So what happens with HMC is that if it's well tuned, it will explore this bit of the density which is around the mean, basically. It will explore this quite well, but it wouldn't be able to go into the funnel because the gradient is not enough for us to know how much to move, basically, because of the high curvature. And all of this, so we're going to explore this well and nothing over here, despite half the probability density being down here. So there is like half of the probability density up and half of the probability density down. So this doesn't sound great. Okay, so what can we do about this? Well, so firstly, let me say that you might be thinking, okay, that sounds like some sort of really funny pathological example that never happens in practice, but we'll actually see that this kind of shape of posterior arises very often in practice when we deal with hierarchical models, especially when we have little data. And I'm going to show an example of this in a few slides. So instead of sampling directly X and Y from this density though, what we can do is we can sample some other variables, X tilde and Y tilde, from a spherical Gaussian. And then we can scale these variables appropriately to recover our original variables of interest. So here, if we sample x from normal 0, 1, and then scale x by e to the power of y over 2, that basically gives us a new variable x that is distributed according to a normal 0 e to the power y over 2. And this is essentially what model reparameterization is. We took our original model and we rewrote it in terms of some other parameters, x tilde, y tilde, and also defined this way of recovering our original parameters. Both of these parameterizations have names in practice, and this is a very common reparameterization from centered parameterization, which is the model, the definition of the model that we see on the left, to non-centered parameterization, which is the model that we see on the right. Okay, so you might, oh, that was not meant to happen. So now you might be thinking, right, that sounds very easy then as a problem. We just put everything in a non-centered parameterization because, of course, it's easier to sample from a spherical Gaussian than from something that looks like that, right? Let's just express all models in a non-centered way and we're all done. But the thing is that it's not so easy when we have actual data. In the case of New's funnel, we don't have data, and it's very easy to see that, of course, that's what our density is going to look like if we non-center. But when we have data, we don't know what the shape of the posterior is. So let's explore this through another example. Let's say that we have, sorry, this thing is appearing in. We have this other example where the data y, we have many data points y that come from a normal with mean mu, SR deviation sigma. And mu itself is given a hierarchical prior where the mean of mu is another random variable theta. And we see that on the left-hand side, we have the center formulation of this model. And on the right-hand side, we have the non-center version where here we only non-centered mu as theta already comes from a standard normal. So we didn't have to change that. So instead of defining mu as coming from normal theta sigma mu, we define, oh, well, I have a typo because in the graphical model is mu tilde, but down here is epsilon. So yeah, this should be mu tilde. So we sample mu tilde from a standard normal, and then we shift and scale to obtain mu. So because this is such an easy example, we can actually work out the posterior analytically. And this is exactly what we did here. So we took each of the two parameterizations, the centered and the non-centered, and we plotted the joint density of mu and theta, and in this case, in the non-centered case, between epsilon and theta, or mu tilde and theta, for different values of q, where q is the ratio between the number of data points n and the standard deviation of the data. What we observe is that when we have low q, which essentially means smaller number of data points, the centered parameterization defines a density that it's quite ill-conditioned. It's very thin. It will be hard to explore, right? We're assuming Metropolis Hastings, I suppose, for this. And then in the non-centered case, we have the something close to the spherical Gaussian that we saw before. But as the data grows, this changes. And now we see that in the centered case, things don't look that bad because this is almost axis aligned, which means that it actually looks like independent Gaussian. It's just with different standard deviation in each direction. While in the non-centered case, we have a really ill-conditioned target density function. So here, this is like very thin and we have a very strong correlation again between epsilon and theta. Right, so what does that mean? It means that it's not really just the case of what our model looks like. We can't just look at our model and say, oh, this variable should be non-centered and this variable should be centered. No, we have to also consider the data, and based on the data, make a decision about parameterization. And this decision about parameterization is also, it's not one or the other. You can have centered for some variables and non-centered from other variables. So you need to do this per variable, this decision per variable. And this is what actually results in, because this is not something that is taken out of the blue. This thing happens in practice a lot, having to decide between centered and non-centered, to the point that you have tutorials such as this one, which is a tutorial on diagnosing inference by Michael Betancourt. Very good tutorial. I recommend it. So this is, see how long of a tutorial this is, and basically what it does is it considers the model we saw in the beginning of this presentation, the 8 schools model, which is just a simple hierarchical model looking like that. And then we try to sample from its centered version, and we start getting weird results, which is all of these plots are different diagnostics that we can run to see if inference is going well. And the gist here is that there is something, we see that something is going wrong here, because we see that the chain, the Markov chain of our inference gets stuck somewhere, like here and here. And we see all these divergences that HMC reports, which I can talk more about if we have time at the end, what that means. But we can run all sorts of diagnostics to see that something is going wrong here. And then the takeaway of this tutorial really is, oh, we have to use non-centered parameterization for this model, because this is what the density looks like for non-centered parameterization when we use the non-centered parameterization, compared to what we were obtaining before. So you can see that this actually essentially looks very much like this funnel, that Mills funnel that we were looking at before. And if we use the centered parameterization, we would explore only the area around the mean well, but not go down the funnel. That's the light red color here. While when we use the non-centered parameterization, the dark red, we were able to go inside of the funnel and explore this part of the density too. Okay, so we saw what model reparameterization is. We saw that it's not very easy to figure out what reparameterization we should use, and most of all, we can't just do this per model. We have to do it per variable in a model. So it's a lot of burden for probabilistic programmers. So the goal of this research really is to free modelers of the need to choose model reparameterization. And the one we're going to do this is by using variational methods to as a pre-processing step to figure out how to reparameterize each variable in our model. Okay, so first step here is you want to see what reparameterization is going to look like in probabilistic programming. On this slide, we have some Edward 2 code. Programs in Edward are, as we saw in the beginning, generative models. So it's a function in Python where we define some random variables and we return the data. And in the centered case, we have just as expected, just theta equals normal 0,3, mu equals normal theta sigma mu, and so on. And in the non-centered case, instead, we're going to sample some other variables, theta, STD, and mu STD from standard normal, and then shift and scale. So it looks exactly as before, it's just in a programming languages, it's just programming languages perspective. Okay, so now basically what we want to do is we want to take this kind of program, because this is more intuitive to write, right? So we're going to assume that the user is going to write a centered models. And we want to take this centered model and transform it automatically to a non-centered model, or at least on demand, like when prompted by the user. And one way of doing this, especially in a effect handler-based probabilistic programming language like Edward 2, is using effect handlers. So what is an effect handler? That is, so it's a programming languages construct which was developed in order to keep track of effectful operations. So for example, if we, in this case, let's say we have the operation read from a file. This is an effectful operation, right? It's not a pure function, because the function opens a file on in your file system and reads from it. So you don't know, it's not a pure function. It does not just depend on the arguments of the function. And effect handlers are meant to keep track of this and make sure that everything is correct. So a handler H can define some other behavior for an effectful operation. So in this case, the operation is read, and we say, instead of reading whatever file we're trying to read, return. So instead of returning, I guess, as a string the contents of this file, return this string, I love PPLs. This results in the following behavior. So if we have a program like this, x equals read file 1, y equals read file 2, print the concatenation between the two, we're just going to have the contents of file 1 concatenated with the contents of file 2. So this is like usual behavior. But then if we execute the same program in the context of the handler H, every time we reach a read call, we are, instead of executing whatever the usual semantics of read is, we're going to go into the handler and figure out, based on the handler, what we should do with this. So every time we have a read, we're actually going to return I love PPLs. So this is going to result in the string I love PPLs, I love PPLs. In effect handling based probabilistic programming, we use handlers to define the behavior of the sample operator. So here we say that the handler H is going to take a statement like this, so V sampled from some distribution, and it's going to define a new meaning of this statement. So the original one will be just bind V to a random sample from this distribution, right? But here we say, okay, no, I actually want to print I love PPLs and then bind V to a random sample from this distribution. And we see again, as with the previous slide, that if we execute this program now without a handler, we just get some, this is just the product of two random samples from a normal distribution. While if we execute it inside of a handler, what happens is, oh, you reach X sample normal 0, 1, we go here, we print I love PPLs, and then we bind X to a sample from normal 0, 1. And then we do the same with Y, and then we print their product. So we're going to get I love PPLs, I love PPLs, and only then the result that originally we printed. Okay, so is that this? Maybe it's a good time to pause for a second if anyone has any questions.
So this is great. So I'm just curious. You seem to have like a probabilistic model here, and So you're reading maybe some data from a file, or what kinds of impurity are you trying to prevent here?
No, so we're not reading from a file. It's just that we're kind of saying, you know what, sampling is an effectful operation. Like before, read was effectful operation. Here we define sampling to be effectful operation, because we can say anything is effectful. So in this,
I see.
yeah, in a language that kind of supports effect handlers, you can make up your own effects, your own operations and your own effects. So we kind of say sampling from now on in Edward 2, and Pyro also works in a similar way. We say sampling is an effectful operation, and we need to find out how to deal with it. There is some default behavior if we don't do anything with it, but the way the language is even built, Edward 2, for example, is that you're going to define a model that looks like this, right? Where you're just going to sample stuff. And then behind the scenes, this model is translated using effect handlers to something that actually evaluates a density. Because if you have something that evaluates a density, then you can plug it into HMC, for example, or do variational inference with it.
I see. Thanks. Yeah. So you kind of treat the random number generator or the source of the stochasticity as something that's wrapped in an effect of some kind, so that you get something more like a pure function. Is that yeah, interesting.
Yeah, and it's sort of, you can think of it as, because we can define these effects, right? That's what we're going to do here as well. We as a user have control over how our program is going to be executed. So you can think of it as, in a sense, a dynamic version of static program transformations. But these are dynamic, kind of. You can just change the meaning of your program at runtime, and you have control over this as a user. That's how you can think about it, I think.
Makes sense. Thanks.
Okay. Right. So back to Edward 2 and how we're going to do that in Edward 2, for example. So as I said, Edward 2 is based on effect handlers, and the way models are transformed for inference is actually by passing them through effect handlers that transform this model to something that evaluates a density. So here, if we instead execute a model, say theta equals normal 0,3, mu equals normal theta 1, if we execute this in the context of this handler NCP that we define just as a simple Python function, what will happen is that when we reach the normal 0,3, it's going to go, instead of sampling from normal 0,3, it's going to go inside the body of this NCP handler that takes a random variable constructor, so normal, takes the arguments to this constructor as some dictionary. And then if it's a location scale distribution, because non-centering only works for location scale distributions, we sample instead from the standard version of this random variable constructor, and then we shift and scale. So this results into this basically executing in the context of this handler is equivalent to executing instead this code. And now, because Edward 2 is effect handling based, the way you would do that is that you're gonna define this as a new model, and we're gonna use that model for inference, which means that now Edward 2 is gonna take this code and, using effect handlers that interpret differently random variable constructors, transform it to a something that evaluates the density. And because now we don't have anymore anything constructing a random variable on the right-hand side of theta and mu, but instead we have mu std and theta std that are normal 0, 1. This effect handler that constructs the density function will actually hit this, and it will define a density on theta std and mu std instead of on theta and mu. It's a bit convoluted, but basically we can nest these handlers. That's the entire idea. So when we nest them together, they give us the desired behavior. So what we did here is we found a way to take a centered model that looks like this, and using an effect handler, transform it to a model that is this, and it's a model with parameters theta std and mu std instead of theta and mu. Okay, that's all great, but this still doesn't answer the question of how do we actually make a decision what should be centered and what should be non-centered, and also how do we do that per variable. Yeah, it seems like we have a lot of work to do here. So that brings me to our contribution, which is variationally inferred parameterization, or VIP. And the way it works is that it's going to use variational inference to find a suitable reparameterization. Okay, so to understand this, first question we want to ask is, given that we have this binary choice between centered and non-centered parameterization, which doesn't seem great if we want to use a gradient-based method to answer which one of the two it should be, right? So we want to find the continuous relaxation between the two, something that allows us to interpolate between centered and non-centered. This is what you see on this slide. So we define the following reparameterization. We're going to, if Z is some random variable with mean, mu, and standard deviation sigma, instead of sampling Z from normal mu sigma, we're going to sample Z tilde from a normal with mean lambda mu and standard deviation sigma to the lambda. Lambda here is not a model parameter, but a parameter that we're going to find using optimization. And it's between 0 and 1, and it's continuous. So you can see that in the case where lambda is 0, this reduces to the non-centered parameterization. While when lambda is 1, it reduces to the centered parameterization. And for values in between, it's something in between. Cool, now we can reparameterize our model with this, and then define a variational family that of a mean field variational family, where the parameters for of each variational parameter are given, the variational parameters of each parameter of the variational model are theta. So these are basically the means and standard deviations of some independent Gaussians that are going to approximate our distribution. And then we also have the parameterization parameters, as we call them. So these are the lambdas, which we have per variable. Now, having defined this, we can try to fit the this variational distribution to our target distribution, and we're going to do this by optimizing evidence lower bound that depends on both the variational parameters theta and the parameterization parameters lambda. So here we're exploiting the conjecture that if variational inference fits well our reparameterized distribution, it means that it's well conditioned, and something like HMC is going to work well on it. That's the conjecture, basically. So this is all a bit abstract, but hopefully this this animation will help. So the idea is that we're taking our distribution, we're defining the variational family, and then during optimization, we don't just try to optimize the variational parameters to fit our target, but we also squish and stretch our target in the same time using lambda. So lambda changes the shape of our distribution, right? Well, changes the reparameterization, so it changes the shape of the target distribution. So we kind of we do these two things jointly, and in this way we find some lambdas that define a parameterization that is, you know, so at least a local minima for this case. And that's what you see on the left hand side. On the right hand side, there is another perspective of the same thing. So this shows the density in terms of the reparameterized variables. So this is x tilde and z tilde. So they move, right? And while here on the right hand side we have the original coordinates. So we have x and z, and we show instead how the fitted variational posterior looks like during optimization. So we see that we start from some spherical Gaussian, and then because we change the parameterization, it actually changes shape, and this defines in a way a more expressive variational family. So lambda defines a more expressive variational family. Okay, so let's stop here for a second again and discuss if people have questions, if that all sounds very abstract, or is it clear?
Yeah, I think so. I'm just kind of curious. It seems like you want to do this for optimization purposes, but also for interpretability as well, since you're rewriting the model that the user wrote down. I'm just curious what the main motivation or the goal here is. Is it to help users understand the shape of their data and how to transform it to be more friendly to the optimizer, or is this just purely for sampling efficiency, say? I don't know if you could comment on that.
I mean, we haven't really seen it in terms of interpretability, to be honest. The main motivation was to improve efficiency of inference. Yeah. So because as we saw with several examples before, the way our model is parameterized can have a really huge effect on the quality of inference, and it can even lead to inference that's just broken, like that example I showed from the blog post of Michael Betancourt. Their inference was just broken. That's how bad it was. So if we have a way to automatically choose a parameterization, this problem at least partially goes away, and the user doesn't have to think about it. But it is an interesting idea to also look at this as through the eyes of interpretability. I don't know how exactly, but it could be. It could be. And so actually, let me maybe show this. So for some of the models that we looked at during evaluation of our approach, we actually plotted, so this German credit block here, this is basically each square says what the parameterization of some parameter in German credit was. The black ones are non-centered parameterization, the white ones are centered parameterization, and the rest are something in between. So I suppose, and this is the optimal parameterization that we found. So I suppose by looking at something like that, we can learn something about our model. I don't know. Maybe we can look for dependencies in some particular way. Say, if, is it the parameters that depend on smaller amounts of data, for example? Are they the ones that need to be non-centered and stuff like that? But I don't know. Again, this is sort of speculative right now.
I see. Thank you.
Okay, so let me then very quickly recap the experiments. So for the experiments, what we did was that we used VIP as a pre-processing step, right? So we run variational inference only as a pre-processing step to find a suitable parameterization. Then we parameterize the model based on that parameterization that we found. And then we run HMC. And we compare performance between purely centered model, purely non-centered model, and VIP. And here the green one is an interleaved HMC, which is an interleaved version between centered and non-centered parameterization, where you kind of take one step in centered parameterization and then transform to centered and take one step there, and like something like this. So you interleave the two. And we see, the first thing we see is that VIP provides a robust, VIP plus HMC provides a robust way of doing inference, because for these models, one of the centered and non-centered was really bad. So here you see that the non-centered, for example, does very badly. I hear the centered does very badly, and so on. And you see that VIP recovers the one that does better. So this is robustness. This is already, it's already quite good, and it already shows that it works in terms of automatically determining reparameterization, the reparameterization of the model, which can be very useful. But the more interesting thing is that for some models, and in particular the German credit that I spoke about a minute ago, neither the centered nor the centered parameterizations gave very good results, while the parameterization found with VIP was much better, 6 times better almost, like maybe 5 times. So, and this parameterization that was found by VIP here, you see it here, right? It's not, it's nothing that an actual human would have come up with, because we don't just have some variables being centered and some variables being non-centered. No, we have some variables where lambda is 0.5. What does that even mean? That's something in between centered and non-centered. So a human would never have come up with this reparameterization, but it does so much better. And yeah, so that's, with that, I'm going to stop and take any questions you might have. I'm very happy to have a long discussion about this if people are interested.
Maria, thank you so much for doing this. This is really terrific work. Let's all give a very warm round of applause to Maria. If you could unmute yourselves and just a round of applause.
Thank you.
I think this was one of our most highly attended talks so far. I think I saw 20 or so people in the middle there. I don't know if you could see the screen, but
I can't, no, I still only see the slides, but thank you. I'm glad. I hope people enjoyed it.
So if there are any questions from the audience, please feel free to unmute yourself and speak up.
Hi, great talk. Can you hear me?
Yes, thank you.
Yes, I have a very simple but important question, and that is, what are the best intuitions that you know in like teaching to convey to people what the difference is between centered and non-centered? like how to best explain it to the uninitiated who knows like modeling but doesn't know that in particular?
Okay, well, there's several bits in this question. So one is how to explain what exactly parameterization means in the general case, and I think it's a bit tricky because we're basically used to think of probabilistic models as in one particular parameterization, and we don't realize that this parameterization is made up. It doesn't mean anything. So here, between centered and non-centered parameterization, they're absolutely equivalent. They define the same thing, but they have so different properties. Their properties are so different. So it's important to understand that the parameterization, the way we expressed our model, is completely made up.
Would you say it's mathematically identical but numerically non-identical?
Yeah, because if we go back, so if we go back to this, these are like in one case X and Y are going to be sampled from these normals, and in the other case X and Y are going to be sampled from these normals. We just sampled them differently. That's it. So it's just a matter of which variables you consider parameters. We don't even have to sample anything from a normal, right? We can sample it from a uniform distribution and then use the inverse CDF to obtain a normal. So that is also another reparameterization. There are many ways of producing basically encoding the same model. This is just the way we encode it. Parameterization is just the way we encoded the model.
Yeah, okay. But let's say somebody already knows what reparameterization is in general. What is the best ways you found to really convey the idea of centered versus non-centered?
I think the best for me, what helped me understand it the most was literally these two graphical models, because it has each of the parameterizations actually encodes different graphical model. So you can see in one case that theta and mu tilde, theta and the parameter basically are independent, but given the data they become dependent, right? Well, in the other case, they're dependent to begin with, and given the data, they're still dependent. And this is actually, it's kind of a little bit fuzzy, really, but this is actually why we see this, where if we have a little bit of data, we prefer non-centered, and if we have a lot of data, we prefer centered, because if we look at these two and we suppose that we have no data, right? If we have no data, then in this case theta and mu are dependent, and in this case they're independent because we don't have any data. So in this graphical model they're going to be independent. So of course we prefer the non-centered parameterization because we want to work with variables that are independent, because then everything is nice and there aren't any weird shapes. We just have independent variables. That's much easier to work with. But if we have data, if we have a little bit of data, we can kind of think of this as like this dependence that is going to be produced between theta and mu tilde is going to be very weak, because observing a small amount of data is almost like not really observing anything. So they're going to be almost, again, it's fuzzy, like don't quote me on this because that's obviously not true, but you can think
okay, so last little aspect from my side. Do you think it's fair to say it has something to do with how tightly you anchor in a standard form distribution, like in a canonical distributional form? How tightly do we anchor our our parameterization into that, because that's one thing that may kind of provide a useful narrative.
I'm not sure I understood what you mean.
Yeah, so like a Gaussian distribution, a Poisson distribution, how tightly do we anchor into that directly, and how much do we loosen from that canonical distribution, the parametric form that we happen to have in generalized linear models and so forth?
I'm still not sure I understand. What do you mean by anchoring?
Well, yeah, less centered, you know.
Less.
So if you look at this, yeah, that's if you look at this slide here.
Mm-hmm.
One way could be to say we are loosening these intervariable relationships in a way to integrate more slack, quote unquote, between what was your parametric form before and the new one. Because a lot of people are confused why you even call it non-centered, and why kind of it's just so confusing to a lot of people. So, and having an effective way to communicate that is pretty important, in my opinion.
Yeah, I also don't know why it's called non-centered, to be honest.
Yeah, and that's the heuristic I found, centered
know.
in a standard form distribution, but that doesn't always hold, of course. Okay, cool. Thank you so much. Beautiful slides, by the way.
Thanks. Thank you.
I guess, yeah, thanks. Again, I'm curious. So you mentioned a little bit about, well, there's, you could reparameterize your model or the data distribution to make the surface of the distribution a little bit more friendly to sample from. I'm curious if this, or what is if you've compared this with maybe a more flexible optimizer. So you could kind of push this into the model reparameterization, or you could maybe use something like adaptive gradient technique to make, because it doesn't seem like this is as much of a problem in general variational inference. Maybe there is some form of like momentum or another technique you could use. I was wondering if you could comment on that.
That's a very good question. I think so. For variational inference, the reason why there isn't a problem is because the way variational inference uses the gradient is different, right? It uses the gradient in order to fit some other distribution as closely as possible to the one of interest. But if the one of interest has a very difficult shape, then even the best distribution, even if we can find with optimization, we won't have trouble finding this best distribution from our variational family that fits our target. But it's not going to approximate it well, because our target to begin with had a weird distribution, right? So like if it was this, the variational, we saw it later, the mean field variational fit just looks like a Gaussian over here. So that's so far off of the actual distribution. Well, the way HMC uses the gradient is to explore this entire shape, but it gets stuck here. And for the adaptive gradient question, that's a very good question. Like, why wouldn't we use in HMC something like that? There is such an algorithm, the Riemannian Monte Carlo, which can do this, but it's not very efficient. So, and it's also very hard to tune. So there is a way of doing it, it's just not very practical. So people end up using HMC and doing reparameterization in practice.
I see. Interesting. Yeah, I mean, it kind of reminds me a little bit of reparameterization in like support vector machines, where you kind of have some some variation along your along certain coordinates, and you'd like to be, there's a dual formulation, so you could either use the optimizer or to reparameterize the space somehow to make it more friendly. But well, I don't know, we probably should wrap up here. It's 10:30, but do you have any questions, Qing Wang? Is there, I know there's a few other people here might. Well, if not, again, please thank Maria. You can reach out to her. We'll put the link to hopefully to the slides on the reading group, and we'll put Maria's contact information in case anybody wants to reach out. Thank you all again for coming, and see you next time.